Last time we discussed about hypothesis testing for proportion, which means population proportion. And now we will see what we do when the population parameter is the mean. So there are two questions here. When we do the hypothesis testing for mean, there are two things. One is, the question is sigma known? Do we know sigma? So if sigma is known, then the distribution z equals to y bar minus mu over sigma over root n. We have this one. And obviously, since we are using here z, the distribution of this one is normal. Okay, we use the normal model. By the way, this is just for your information, because in this book, they are not using, it's not in the book, so this is just for your knowledge, but it will not be part of any in the test or in the final exam. So whenever you do hypothesis testing for mean in this course, the assumption is sigma is unknown. Okay, this is our assumption. We are following this path. And when sigma is unknown, since this guy is not known, then the distribution becomes, instead of the standard deviation of y bar, we use the standard error of y bar, s over square root of n. And the distribution of this one is student's T model. Okay, so these are the two cases. And as I said, in this class or in this course, we are assuming this one, sigma is unknown. So do not worry about this, but for your knowledge, I want you to mention this one. Okay, but in general, if I give you any problem to do hypothesis testing about the mean, always the assumption is this one. In this course, okay, because we are just using the T model. Therefore, for this class, if we have a problem about proportion, we use Z. If we have a problem about mean, we use T model, assuming the sigma is unknown. Okay. Therefore, when the sigma is unknown, the distribution is given here. It is a student's T model. Therefore, we call it one sample t-test because we are testing a one sample mean. And so the test is called one sample t-test for the mean. Again, here is the assumption. We don't know the standard deviation, the population standard deviation. That's why we are using the T model. Otherwise, we would have used the Z table or the normal model. Okay, so what is this one sample t-test for the mean, or what are the procedures? So the first thing, as always, we have to check the assumptions. Well, what are the assumptions for one sample t-test? This is the same with one sample t interval. So to construct an interval, for the mean, well, it's given by y bar plus or minus the margin of error, which is given by, so this has to be t again, z asterisk n minus 1, t asterisk n minus 1 times the standard error of y bar. This is the confidence interval. And to construct this confidence interval for mean, we had assumptions, and those assumptions are, one is independence, independence, and the second one is randomness, and the last one is near normal. This is T. Okay. All right, so these are the assumptions for constructing a hypothesis, the confidence interval. So one thing that we would like to check is if the sample, when we select a sample, were they selected randomly? And are they independent from each other, or there is influence? So this usually, if it is random, if they are random, if you select them randomly, usually this independence is guaranteed. So if you see in the problem that the sample is selected randomly, then both these assumptions are okay to assume these are satisfied. And the near normal, if you have the data, if you have the actual data, then you can construct a histogram. You can construct a histogram, okay, for using the data. So if it is not too skewed, you don't expect it to be perfect, but if it is not too skewed, then you can, it's good to go with this assumption or with this model. So the near normal, last time I think I gave you some rule of thumb. If the data is, if n is less than 15, then we want the histogram to be close to perfection, because since our sample is very small, we want this histogram to be close to perfect, close to symmetric and unimodal. If n is between 15 and 40, then it's okay if it is a little bit, not a little bit, but slightly skewed, either to the right or to the left. And again, if n is greater than 40, now here we assume the sample size is kind of big. Therefore, we can let the histogram to be more skewed than this one. So as n goes up, as n increases, then we have more space to account for the skewness and for the outliers. Okay, still we can use the T model as n goes bigger and bigger, even if the histogram is skewed, because the central limit theorem, last time, if you remember in class, we used the simulation is 0, 1, 0, and so on and so forth. And when we do the simulation, even if the histogram, original histogram of the data was skewed, the histogram of the y-bars becomes more or less normal, unimodal and symmetric as n increases. And that's why we are using, even though it's skewed, since the histogram of the y-bar will become kind of normal. So we have that guarantee because of the central limit theorem. All right, so here are the assumptions. And once you check the assumptions, and then you write your hypothesis test. And the null hypothesis is always given by this one.
Which letter it is when it has the greatest 40?
This one, it is n. Okay, let me, this one.
No, yes, that one.
Yeah.
It's n?
It's just n, yeah.
Okay, thank you.
Yeah. We are talking about the sample size. So when n is between 15 and 40, when n is less than 15, when n is greater than 40. Yeah. But again, these numbers, they are not, it's not strict. Sometimes they will tell you like when n is greater than 30, then you don't have any problem. This in any statistics, in many statistics books, you will see, you will find this one. When n is greater than 30, then we assume the sample is not is big, is large enough. And in some books they will tell you if n is greater than 30, then instead of t we use z, which means y bar minus mu over s over square root of n. Of course, this is t. The distribution of this one is t. Did I mention it? Yeah, it's the same with this one. But as n gets bigger and bigger, this t gets closer to this z. Therefore, when n is greater than 30, they will tell you it's good to use the z table. But since in this book they haven't mentioned it, I'm not going to tell you, or I'm not going to ask you to use this one. Just always use the t model for this class, okay? Whether your n is 100 or it doesn't matter, or 1000, just use the t value, the t table, okay? But the value, it will give you more or less the same value, okay? It will give you exactly like this one, because when n increases, this value will be the same with this z value. All right, so we have the hypothesis, and then just like with proportions, we have the alternative hypothesis. So one option is mu not equals to mu sub naught, or mu greater than mu sub naught, or mu less than mu sub naught. So we have three options again. This is the two-tailed, and these two are the one-tailed. Let me use two-sided, because here we are using the side term, so two-sided. And these two are one-sided, okay? So, and then we have the standard error of y bar. So when the conditions are met and h sub naught, the null hypothesis is true, this statistic follows a student's t model with n-1 degrees of freedom. And since we know now this follows a t model, or student's t model, we use the t table to find the p-value. Because all this model it's important, because we are going to need it to find the p-value, and this p-value is the one that we use in order to decide whether to accept, to reject the null hypothesis or fail to reject the null hypothesis. Okay, so this is the final decision. So all our evidence will be this one now, finally, because the p-value we use, it comes from our sample. After all these calculations, finally we arrive at this point, and we use this one to decide. So if you notice here, for confidence interval, we will comment later, but for confidence interval, we didn't need this one. And the model, we used the model just to find the margin of error. But here the model is very important. And here we are saying when h naught is true. So under this assumption, we have a model, just the same with proportion as well. Now we are collecting a sample, and we are trying to check if our sample is consistent with this model, because this model is true only under this assumption, under this null hypothesis. But when this is false, probably this is not true. Well, it's not true, not probably. This is not true. Therefore, we are trying to see if our sample fits or is consistent with this model under this assumption. So when our sample is consistent with this one, when we don't reject this one, our sample is consistent with the model. But if we reject this one, our sample is not consistent with the model. So we are starting with the model and we are checking if our sample fits in the model or to the model. But confidence interval is the other way around. We start with our sample and we create an interval centered around the mean of our sample. Just like this one, the confidence interval is centered around our mean. Okay, so here we have an example. So this is about salary of secretarial staff in California State Universities. So the average salary is given by this one. So here I will put the given values. Mu equals to 47. Oops. $47,500. So this is my H sub naught. And we examine whether the mean salary for the secretarial staff at USULA is different from the state mean. So the state mean is this one. In the whole overall, the state in California, the overall average is this one. And in this specific university, we are trying to see if the mean is different from this one or not. So what do you think is our alternative hypothesis now here? Mu not equals to 4750. So this is the first step. I have to write it. So this is our first step. And here we have the hypothesis. We stated our hypothesis. And the second one is, of course, the model. And here, well, it doesn't mention any randomness, but we will assume this sample is selected randomly. And since we don't have the sample, we don't have the data, I cannot check the near normal, but we will assume that one, okay? And another thing is the number n is greater than 30, greater than 40. So even if it's skewed, unless it's too much skewed, it's okay because the sample is big, somehow bigger than 40, okay? Therefore, we will assume all the conditions are satisfied. So when the conditions are satisfied, we have T n minus 1 equals to y bar minus mu over the standard error of y bar, where the standard error of y bar is given by s over square root of n. So in step 2, you only need to mention this. You don't, this one and checking the conditions. You don't need to do the calculations, okay? And then step 3, you do the calculation. So here, y bar represents the mean of this 64 people members, and y bar is 49,000, and n is 64. Now, what is the degrees of freedom? This is given by n minus 1, and that is 64 minus 1, which is 63. And what is standard error? This is S over root n. Well, S is given, by the way. It's here, 62. So S is 6200. So this is 6200 divided by square root of 64. And let me use calculator. I got 775. So this is the standard error of Y bar. Do not forget this one. Don't use this. This is the standard deviation of the data, the actual data of these 64 people. Okay, these 64 staff members. But standard error means the standard deviation of Y bar. Well, we don't call it standard deviation. I mean, in this case, it's standard error because it's S over square root of n. So always use this one, not that one. This is for Y bar. This is for the Y's or the actual data. And the next step is to calculate the test statistic, which means this one, to calculate this guy. Because I have all the ingredients now, so I can calculate this. So T n minus 1 is Y bar, which is 49,000 minus 47 divided by the standard error of this, which is 775, and I got 1.94. When you round it to two decimal place, I got 1.94. All right, so what next? Now I have this. What do we need next? We need to find the p-value now. So this is the calculated t-value or the test statistic. Now, before we go to the p-value, now let's look at what this means. Suppose this is the graph of T 63 degrees of freedom. And if we assume the null hypothesis is true, then here we have mu naught, which is 47,500. Well, the t-value for this one, the t-value is 0 because the center is 0, the standardized value. And the calculated value, what we have here is 1.94. And this is a t-value for 4,900.
Excuse me, from where do you got the T63?
Oh, 63? This is the degrees of freedom. Degrees of freedom. Yeah,
okay.
This one.
Got it.
Yeah.
Thank you.
So this is subscript like this one. You see, that's how we write it. T, whatever the degrees of freedom. If it is 10, sub 10. So this is subscript.
Okay, thank you.
So maybe I wrote it the same. Yeah. Okay. Now, from the Z model or from the normal model, if you remember, we would use these values as a distance in standard deviations from the center. So what we are saying is our Y bar, which is this guy, it is some at this point. This guy is 1.94 standard deviations far from this center. Now the question is, can we say this is far enough to reject the null hypothesis, or it's not that far? So when we say far enough, how do I measure that far enough? And that's the question that we have to decide.
P-value?
Yes, that's the p-value that we use. Therefore, what is the p-value now? How do I find from this graph? Well, the p-value is the probability under when H naught is true, the probability of obtaining or finding samples or data like our sample, or more extreme than that. So more extreme means you go to this direction, or from the other side, we have negative 1.94, the same value like this one, but symmetric, negative, the opposite number. So what is the probability to find samples somewhere in here or on this side? What I mean by this is, let's say you pick another sample from the same population. So what is the probability of getting another sample which will be somewhere in this area, given H naught is true? Now, in this case, we are assuming H naught is true. Okay, we are assuming H naught is true. So given H naught is true, what is the probability of obtaining samples somewhere in this area? And that's the probability. So given H naught is true, if this probability is big enough, then we are not outside of the range, or we are close to the mean, the center. But if this probability is very small, we are saying it is very rare to obtain such sample given H naught is true. Okay, it's kind of, it's not, I mean, it's not that easy to find such samples. And that's why we reject H naught. If the p-value is small, we reject the null hypothesis. It should be either not true, or we reject H naught, or the sample that we have, it's very unlikely to get such samples, which means something happened when we obtain our sample. Okay, so to find H naught, the p-value, this is p-value. Of course, this is p-value, half of it. Okay, so to find p-value, I'm gonna go to StatCrunch. So we go to stat, calculators, and then we go to T.
We can't see
Oh,
StatCrunch.
yeah, okay. All right.
For the test, are we going to be able to use a StatCrunch to find the p-value?
Yes, yeah, you can use StatCrunch. You don't have to worry about that.
Okay.
Yeah, because you will be in front of your laptop, so you don't have to worry about that. You can use anytime StatCrunch. But it's good to know even the table. Like, it's up to you, of course, but it's good to know both of them. All right, so here, finding one area is good enough because it's symmetric, so you just multiply it by 2. So either find the right side or the left side. Now I'm gonna find the right side. So our t-value, the calculated t-value is 1.94. And don't forget here, the degrees of freedom, you have to provide the actual degrees of freedom. So it's 63. And then we have this number, which is 0.028. Okay. .028. Here we have p-value equals to 2 times 0.028. And this is 0.056. Okay. Now the next question is, what is our alpha? Now remember, if it is not provided, if it's not given, we use alpha equals to 0.05 if it is not given. But in this case, we have alpha 0.1. Okay, so we need to, we have to use this alpha. So p-value is less than 0.1, which is, this is our alpha, and p-value is right here. Now what do we say if this is the case? When p-value is less than alpha, then
We reject the null hypothesis.
What do you think under 0.05 if alpha was 0.05?
If alpha was 0.05,
Yeah. I will put on the side. If alpha was 0.05, what would happen?
we wouldn't reject the null hypothesis.
Yes. So the only thing you need to do is just compare this. So you can change alpha depending. And one thing, be careful when you do such research, if it ever happens in your work or whatever, do not decide alpha after obtaining p-value. Don't do this, don't manipulate this, because you have to decide what your alpha has to be at the beginning, depending, or like any criteria, you decide what your alpha is at the beginning. And then you do the calculation, you collect your sample, and then you calculate your p-value from your sample, and then you do the comparison. But after finding the p-value, if you choose this one, you can choose a value that such that you can reject the null hypothesis if that's what you want, or fail to reject the null hypothesis if that's what you want. That's not the case. That shouldn't be the case. Choose your alpha in advance. Okay. So if p was this, then p-value would be greater. So in this case, fail to reject H naught. Okay. Now coming to this one, coming back to this, what is our conclusion now? So okay, the decision is we reject H naught. We don't agree with H naught. And what was it? H naught? H naught is the mean salary of the secretarial staff in USULA is the same with the state salary, average salary. And our alternative hypothesis is that's not the case. It's not equal, or it is different. So we don't agree with this. We reject this equality, which means the mean salary of the staff, the secretarial staff in this university is not the same with the state mean. So I will write here to conclude that well, I think this is better to, if we write it different instead of higher, since we are So I will put different. Okay, so that's the conclusion in the context of the problem. So always, after taking this decision, after rejecting or fail to reject the null hypothesis, you have to write it in the context of the problem. Okay, do we have any question?
So you say if it's greater than 0.05, fail reject, but if it's less than 0.10?
Yes. Yes, so the idea is...
What about if it's greater?
If it's greater, it's this case.
Okay.
If it's greater, we fail to reject. So what does it mean when it is greater? Okay, let me add more space here. So suppose you have alpha. Let's start with alpha now. Suppose alpha is 0.05. And on both sides, we are using the two-sided 0.25. And the same on this side, 0.025. Now, if you remember confidence interval, given, let's say, 95% confidence interval, this will be your interval. This would be your interval. So we are saying in confidence interval, the population mean, since we don't know the population mean, will fall between this. We are 95% confident the population mean will fall in this interval. That's what we say with confidence interval. In this case, we start with alpha, give alpha given 0.05. On both sides, we have this half-half. And after you collect your sample, you do all the mechanics, and you have a p-value now. You calculate your p-value. When p-value is large, which means if p-value is, if p-value is greater than 0.05, suppose. What does it tell you in this graph? So p-value comes from the t calculated, right? Or from the mean, because the procedure is to find the p-value. The steps are, you have y bar, you start with y bar is from your sample. You find this calculated t-value from your y bar. So this value is the standardized y bar. You are standardizing your y bar. So all these are from the sample. And then using this guy, you find the p-value. So if you follow the steps, the p-value is from the sample. It comes from the sample, which means from this y bar originally. So if p-value is big, if p-value is larger than 0.05, sorry, then it means our y bar is inside this area, somewhere inside this area. Okay, if p-value is greater than 0.05. But if p-value is larger than if p-value is smaller than 0.05, then y bar is somewhere outside this area. Okay, and this is why we are rejecting the null hypothesis. So if it is outside this area, and assuming at the center we have mu sub naught, we're assuming h naught is true. So we have at the center mu sub naught, which in this case is 47,500. So if y bar is in this area or in this area, we are saying y bar is far enough from mu naught, mu sub naught. But if y bar is inside this white area, inside this interval, then we say y bar is not that far from mu naught, So it's possible because randomly, since we are selecting our data randomly, it's possible to have y bar somewhere in all these areas. Okay, so it could be because of randomness that we got this y bar, which is some distance from mu naught. So it's possible within this interval. But outside that one, it is kind of rare to find y bar given mu naught is true or h sub naught is true. Therefore, always when p-value is smaller than your alpha, reject the null hypothesis. When p-value is larger than your alpha, fail to reject the null hypothesis. Okay. Any other question? So in constructing confidence interval, well, both of them, this confidence interval and hypothesis testing, they are two approaches or two techniques or two methods that we use to answer the same question. So we have one problem or one question that we are trying to answer, and we have two different approaches to answer that question. And that question is, in the case of proportion, it's about the P population proportion. In the case of mean, it is about the population mean. So we are trying to figure out what these two are. Okay, so in the case of interval, we don't know these parameters. They are not given. We don't know this. Even there is no hypothesized value. So what you do is you try to estimate or approximate or try to find the interval for these two parameters, right? So since we don't have any idea, we would say we are 95% confident that the population proportion or the population mean will fall between this interval. Okay. And in the case of hypothesis test, what we do is we would be given some hypothesized value. We would be given some p equals to p sub naught or mu equals to mu sub naught. So in this case, we have some hypothesized value. Is it possible that the p is p sub naught? Or is mu equals to mu sub naught? So we try to check this if they are true. Okay, if these two are true, or if we agree. So to answer this question again, we collect data, we do all the steps that we did, and we agree or not agree with this hypothesized value. So both of them, in both cases, we are trying to answer the same question. Okay, so it's just looking at a problem from two different perspectives. Confidence interval. Here, yeah, so it is a data-centric. Earlier, I tried to mention this one. It's a data-centric, which means the center is the statistic computed from the data, which means, I don't know if I can put some space here. Oops. So here what we do is we start with our data. The reason why we call it data-centric is we start with y bar. And by adding and subtracting the margin of error, we create the confidence interval. This is what we call the confidence interval. So you have y bar at the center. And then you find two upper limit and lower limit for your interval by adding and subtracting the same value. So the center is your data. Y bar means your data. And it's always two-sided. It's always two-sided. We don't have one-sided interval. Okay. But hypothesis testing, we have both one-sided or two-sided hypothesis testing. Okay. How do we? All right. Yeah, I think it's okay now. But hypothesis testing, it is a model centric. It's model centric. And the reason why we call this one is you start with a proposed parameter, which is, let's say, for example, we say mu equals to some value mu sub naught. So this is where we start. And we said when this is true, when the null hypothesis is true, we say Tn minus 1 y bar minus mu sub naught over the standard error of y bar follows a T model or student's T model. Sorry. So this is the assumption that we start with. Instead of starting with our sample, we start with this assumption. Okay, so we have the hypothesized value, and under this condition or under this hypothesis, we have this model. Okay, we have this model in this specific example or in this hypothesis for me. So after having this hypothesis or this model, what you do is you collect data, you do all the procedures, and you see if your data fits to this model. Okay, if your data is consistent with this one. That's what we are trying to check. That's what we do. Therefore, this we call it a model centric. It is around the model. You start with the model and you check if your data fits to the model or is consistent with the model. So we have a two-sided test, and when it is a two-sided test, it has the same meaning with confidence interval. Okay, it's you can still reject a null hypothesis based on high confidence interval, even if you don't find the p-value, but by just constructing a confidence interval, you can reject the null hypothesis. Now, how can we do this? So let's create a confidence interval for the example about the mean. So we have y bar, which is 49,000, and we have standard error of y bar, and I don't know what that was, 775. Okay, and since alpha is 0.1, we are given this alpha. So the confidence level, which is C, has to be 90%, which means 1 minus this one is 0.9, and converting that one to percentage is 90%. So we are trying to construct a 90% confidence interval. And based on this confidence interval, confidence level, we need to find T n minus 1, which is 63 of this 90%. So we use the table to find this value. So here, do you see the StatCrunch now? Am I sharing that one as well?
Yes.
Yes.
So here, let me go the in-between. The in-between area, we want it to be 0.9, and we are trying to find these two critical values. And those values are negative 1.67 and 1.67. So going back, here we have are negative 1.67 and 1.67. The reason why I'm writing both of them is in some of the problems that you have in homework, they will ask you to write both of them. So in case if that happens, this is how you write. But in general, you don't write this. You just write one of them, okay? Because we always know they are opposite to each other, so you don't have to mention or write both of them. All right, so the confidence interval is given by y bar minus the margin of error, which is given by t asterisk times the standard error of y bar, comma y bar plus t asterisk times the standard error of y bar. So if we compute this, substituting all the values, what do we get? We have 4900 minus times 1.67. So the lower bound is 47705.75, comma, the upper bound is 50. Wait. Okay. Yeah. So we have this one. I got this. I don't know if I got it right or wrong. Yeah. So we have this. So what do you think about this is our confidence interval now. So we have confidence interval 90% with 90% confidence level. We have the confidence interval from 47705.75 to this number. So we have a hypothesized value. H sub naught says mu equals to 47. Was it 500? I guess. We have this hypothesized value. Now, based on this one, now we're not following the hypothesis testing procedures now. We're not using the p-value or stuff. I will just use this confidence interval. So this is from our data. From our data, we have this confidence interval. With 90% confidence level, the population mean of the specific university falls within this interval. So can we say our data is consistent with this model or with this null hypothesis? What I'm trying to say here is because this number doesn't fall in this number, in this region, okay? The lower limit is bigger than this number. Therefore, this number falls outside this area. So just because of this one, using this confidence interval, I reject the null hypothesis because this number, the hypothesized value, falls outside the number, outside the region, outside the interval. All right. And one more thing, when you deal with proportions, we have these two cases. For intervals, we use the standard error because we don't have hypothesized value. But for hypothesis test, we use the standard deviation. The reason is because we have hypothesized value here. We have H sub naughts P equals to P sub naught. And we use this as a population parameter. And we use that one to calculate the standard deviation. But here, since we don't have any value like this, we use the sample values or the sample proportions, and we call it the standard error. So be careful in this one. When you deal with proportions, for intervals, always use this one. For hypothesis, always use this one. But with, in the case of confidence interval, we don't have that problem. Always we use the standard error of the mean. Now, the next important thing here is errors. We have to consider, because always when you do decisions, there is possibility that you can commit mistakes. So here in hypothesis testing, there are two errors that we could commit, and those errors we call them type 1 and type 2 errors. So type 1 error is rejecting H naught or rejecting the null hypothesis when it is in fact true. So in reality, the null hypothesis is true, but because of lack of evidence, you reject the null hypothesis. In that case, you are committing type 1 error. Okay, and the second one is fail to reject H naught, while in fact H naught is false. Well, when H naught is false, we're supposed to reject it if we knew it was false. But because of our evidence, because of our data, it wasn't sufficient. We failed to reject H naught. So this is another error now, and we call it type 2 error. So this happens like in medical tests and other types of tests. Whenever, I mean, in every type of decision, even in trial, in court, for example, you have a defendant. So H naught, defendant is innocent, and H sub A, the person is guilty. Okay. So if you have this hypothesis, when the jury, when they decide, they depend on the evidence. Okay, they didn't see him, the person, so they depend on the evidence. So suppose the person is, in reality, in fact, the person is innocent, but there was enough evidence to convince the jury to convict him guilty. Okay, so in this case, H sub naught is true. The person in reality, in fact, the person is innocent. But because of the evidence they collected, whether it was his or something else, because of the evidence, the jury was convinced and they convicted him guilty. So in this case, they are committing type 1 error because they reject to accept this one. They're not accepting this. They're not accepting the person's innocence. They're rejecting that one, even though the person is innocent. And the second one is the person actually committed the crime. In reality, the person did the crime. But because of lack of evidence, they didn't convict the person. Okay? So the person goes free, even though the person did the crime. And this is another error which we call type 2 error. So always when you do decision, you try to minimize both of them. You don't want actually, but you wanted to make both of them 0, but that's not possible. It's not possible to avoid these 2 errors. The only thing that you could do is minimize those errors. Okay? And the problem is when you minimize one of them, if you wanted to minimize this one goes up. This error goes up. And if you wanted to minimize this one goes up. So the best way to do is to balance them. That's why we use usually alpha somewhere around 0.5 or 0.1 or 0.01. We don't go far from that one. And this is what we call the type 1 error. This is the probability of type 1 error. Okay? Here it is. Probability of type 1 error is alpha. The alpha that we use, that is the probability of us making type 1 error. When we do this decision, the probability to make type 1 error is given by alpha. The second type is given by this. The probability of the second type is given by this beta. But this beta, it's not something easy to calculate it, so we don't deal with that one. But usually, the idea is to keep them somehow balanced, okay? And here we have, I put this table. This is very helpful, I guess, to figure out what type 1 and type 2 errors are, because this is easier to memorize instead of, rather than this definition and stuff. Because they are, most of the time, they are kind of confusing. So what is type 1 error? Type 1 error is, in reality, H naught is true, but your decision is reject H naught. So here is the decision. So you reject H naught, but it was true. So you are committing type 1 error. And you reject H naught, and actually it's false. So that's a good decision. Fail to reject H naught, that's your decision. You don't reject H naught, and actually it's true. So again, good decision. And the last one is you fail to reject the H naught, but it was false. It was supposed to be rejected, but you failed to reject it. And this is type 2 error. So you have these two corners or two squares, type 1 and type 2, and these are the correct decisions.